Okay, we're back for real this time. Sorry, I had some audio issues, which I think they're not fixed. All right, so we're really back with more coding content. I hope I'm loud enough. I think I should be. Nah, this seems okay. All right, more coding today. More coding. But we're not doing the old repo anymore, which is kind of funny because that's probably why I had the audio issues. What ended up happening is I kind of gave up yesterday, and I actually ended up downloading that full data set and retraining a model from scratch. So that part worked. So I had to download the 1.6 terabyte data set, and I had to switch to Linux on this computer, which is probably what broke my mic settings, I think. But in any case, today we're back with the MIMO series, right? So the series where we sort of recreate this grad school project of mine. And I think last time we did a lot of progress with data. I see some data. I generated some data offline here. So we have train and validation data now. And I think we enabled actually full-scale training, if I remember correctly. Yes, I do. So I'm already on a new branch. Let's do a quick overview. Let's see if we have the diagram. We should have it here. Oh, here we go. Oh yeah, and we also did this data splitting logic last time. Because we ran out of RAM, I think, because the way NVIDIA implements their toolbox is not that great. Okay, so we have a bunch of data now. We know we can train a model. Let's see, where are we overall? Pretty good progress, I would say, overall, right? So we have diffusion training, signal processing, PyTorch, UV, pre-commit hooks by project. We don't have typing or logging. So there's a few more Pythonic things to do. We have a loss function. We have data generation. We're missing the big piece though, which is inverse problems and model inference, right? Like what are we going to do with this model? I think we talked about this somewhere in this diagram. We talked about here it is. We talked about the difference between training a score-based model and using it, which is also called inference with the score-based model or a diffusion model. So actually I'd like to implement this today. Sampling synthetic data, okay? From a score-based generative model. And we're gonna do it the way I did it in the paper, which starts from pure noise and is sort of supposed to produce synthetic data. And we're gonna monitor this. We'll write a Python function, and we may also add some logic to monitor this during training, because you kind of want to see during training how does the quality of the generated data improve or stuff like that. Now, in order to implement this, we're gonna need the paper. This is actually a bit trickier because it's not actually in the paper, right? So let's see, MIMO, where is it? Here it is. Channel estimation with score-based generative models. So now we actually don't have this type of sampling, pure synthetic data sampling. And last time we looked a lot at how the channels look like. But actually we sort of do have it here. So actually the update would be closer to equation 4. We don't really have an algorithm for it though. So what we're gonna do is we're gonna have to figure out, which may be tricky actually. It's probably easier to figure out what the parameters are, but we're gonna have to figure out, here it is. So this is the real update. We're just gonna cut this term though, to not make it conditionally sampled. Okay, so we're just gonna leave the 3. So the current channel becomes sum alpha times the model prediction at the current channel, plus some added noise back, which starts to make a lot of sense now, actually. This is pretty close to this, right? So I start from pure noise. I pass it through the model. Remember, the blue thing is the model here. I get the purified version, but then I add some noise back. The problem is we're gonna have to figure out what these constants are and what their schedule is. Let's see, what do we do in the paper here? What do we say? Oh, okay, so we have some formulas here. Okay, this is a lot closer. So we know it's square root 2 beta times some alphas. Aha, we know it's a geometric progression. So alpha I will decrease. R is less than 1, right? So the more I multiply with R, so alpha 0 is just alpha 0, alpha 1 is alpha 0 times R, alpha 2 is alpha 0 times R to the second. Okay, so we know there's some exponential thing here. There's also a sigma zi, which I don't remember. Let's see, it's hyperparameter discussion section 4. Yeah, so we're pretty close. But it's actually sigma. Okay, so I think we set sigma zi constant. Okay. Yeah, and that's it. This looks pretty much it. And then for the conditional sampling, we just have to implement this other term, and then that's also it. So maybe we can think about how to write this update rule maybe in a smarter way, so we don't have to write, we don't really need two functions, right? Doesn't look like we need two separate functions. So okay, so we just have to implement an update. So how should we write this? We're basically going to implement this, right? Except we start from some oh no, sorry, this zi is also sigma zi. Okay, so we have to look, do we say what values we use, or are we gonna have to guess them? We may have to guess them, but we know how to guess them because we're gonna have training data, or we're gonna have validation data, so we can sort of visualize how the channels look like and if we get them right. Now let's try to find these in the paper though, section 5. I need an alpha, beta, and a sigma. This is not the same alpha. This is a bad where. Oh, here it is. So no, it's not this. No. Actually, we don't have details on the sigma. Is it the sigma? We also need to know what we trained the model on. Aha, it is. Oh, here it is. I see it. So sigma zi is a noise level selected uniformly at random from a set of values. Okay, so we need to build this set, and I'm pretty sure it's... Is it exponentially spaced or is it geometrically spaced? Yeah, oh, I see, here it is. Inference noise level, same as what S was trained with. Okay, so we can choose, okay, this is what I was looking for. So first we need to go and see what we trained this with, and then we need to descend on the noise levels, right? Because as I increases, the convention here is that as I increases, this power should decrease. Because towards the end of the or this is how it should be. I think that makes sense. So the first noise level is the highest. Yeah. Okay, and then we run inference exactly on these same noise levels, and then we repeat the step m times at the noise level, and then we descend on the noise level by just changing the sigma and also incrementing the alpha 0 coefficient. And the 2 beta is another multiplier for the noise, a separate one. Which can probably, honestly, this is just, well, I guess technically it can't be absorbed because this has to be exactly like in training, but yeah. Okay, so this is sort of what we have to do. So we have to do exactly this, except of course the numbers I made up here. So let's write a clearer picture of this then. Let's write something nicer, right? So we're gonna start noise, but it'll be, do I have a sigma here? No, I do not have. I'll just call it S. Actually, this is not great because I can't do math here. Yeah, so except this is just sigma Z0, SZ0, okay, times IID noise, okay? Then we're gonna add back, okay, so this is score-based model. So we do a forward pass, then we need to add back square root of 2b times a times r times SC1 times noise. Okay, we add this back. Then we repeat. Okay, so we need more accurate numbers here. So let's see. And then I go through the model again. No, that's not how I go, because I do a plus here actually, right? Because it says I sum them. Right, so I take the previous estimate and I sum both the noise. Okay, so it's a triple sum, right? Plus, plus, plus. I'm ignoring this conditional term where that's the fourth term that we'll implement some other time. But just to get, okay, so it's a triple sum then. So this thing here actually goes here, and it also gets summed with this. Let me see here. How can I get this here? There we go. Now I just need a triple sum box, which can be something like this plus well, actually they should go in the node here. So this should go here and here. And that's it. This thing gets repeated now, okay? Because now I have my output, which is the output of the triple sum. Again, I go through the model, the same model now. And I get out and I want to sum noise, except now the noise decreases a bit, and the only way it decreases is because it's times r to the power of 2 now, and SZ2. So there's a doubly, yeah, there is some fiddling to do here, right, with the constants. Yep, that's how it is, right? Because I sigma, yeah, I want to add less noise. Do I also anneal my step size? Let me look at the other paper we have then. Compressed MRI generative. think we have better formulas here. Somehow I'm not happy with the formulas I wrote in my paper, or the paper which I did after this. Okay, this is with the fixed coefficient, so this is eta square root 2 eta. So maybe I'm overcomplicating it. Maybe it really is like this. Yeah, I think I am, because there is no beta. So beta is something I made up. So this should be 1. So then it's just... Oh, sorry, I forgot to multiply the score term. Oh, yeah. Sorry. So okay. So beta is 1. So square root 2 times this. But where is the annealing part, though? I wonder if I have too many coefficients. So there's also a multiplier here. I forgot, right? It's multiplied with, it seems like it's A times R in this case. And then it goes to the sum. Right. And now this becomes multiplied with A times R squared. Yeah, these coefficients are definitely in sync. Okay, so let's do the basic one. You know what? Maybe we just do the basic one. Then if it works, it works. If not, then we'll... Now my paper technically has... But I don't need to match the noise levels though? Like, is it SC... No, it is. Sorry. Okay, here it is. Okay, so no, this is right. Okay, so it's psi t here. This also decreases. Oh, okay, so we're good then. This is SE1, SE2. This also changes. Okay, so then B is just 1 by default. Okay, right, good. So then this also happens here. So then the input again goes here. And again, we get another estimate, and dot, until we reach a very tiny SC. And then at the final step, we no longer add the noise, which I think there's detail I didn't actually implement. So this will be good. Yeah, we still add a bit of tiny noise in my paper in the original implementation, which I think is a mistake. Because at some point you reach ... and at the final noise level, let's see, can we get it? Yes, we can. So when you reach the final noise level, so this will be A times R to the N, you don't want to add noise anymore, okay? So this will be ... It continues this way, right? Because we don't have room to draw. And then we can call this final output data, right? So now we magically went from noise to data, right? Because we start from SC. Wherever I say times noise, that means unit power noise. So we're going to use torch ran then. And this is called anneal Langevin dynamics. Annealed, okay? So inference with annealed Langevin dynamics. Langevin dynamics itself is the process where you keep this constant, where you just add the same amount of noise. Actually, let's look that up. This is a good thing. I think the step size still... No, maybe it's... Yeah, so Langevin dynamics is just everything is constant. Or rather, the step size... Oh, no, sorry. The step size is constant. Okay, well, these are very hard to read. I wish we would find something. So it's one of the bases of score-based. Interesting. So even Wikipedia knows this, right? From linear dynamics, we have this differential equation where we multiply the gradient epsilon, which is the useful information, which in this case is given by the score-based model, plus square root of 2 times epsilon, which we recognize easily now, right? Right, because we multiplied the useful info with a times r, and then square root of 2 times a times r, except I introduce my own beta here, which should kind of be 1, times zi. Oh, okay, and the noise is constant, okay? So Langevin dynamics would just do times noise, and it would even keep the step constant. Like Langevin dynamics would, everything would just converge, but then maybe at the final step you still don't add noise there. But we're doing the annealed version, right? Where we decrease our steps and the added noise power as we go along. So this kind of makes sense. Another optimization way to draw this, how should we think about it? Yeah, like if you're trying to maybe, let's see, I'm gonna try to draw some optimization here, which is gonna be pretty hard actually, right? So let's say we're trying to optimize a surface like this, where the shade of green means a higher value. Okay. So then, and I start from somewhere here. Okay, and now I know the gradient points in this direction, okay? So what I do is I take a gradient step. This is probably not the best drawing, but I take a gradient step which is scaled towards the direction. The surface is pretty easy though, because it points clearly towards the minimum. Assuming there's also a gradient of color. Then I also, so I take a scaled step in this direction, then I add some noise, which kind of throws me around a circle, okay? So when we say we add noise, okay, so we can say adding noise places us on a circle in high dimensional space. Let's call it a sphere then, on a hypersphere. Okay, around the original point. Okay, so then I start, so then I can say I started from init and I get to new. Because I land somewhere randomly. Okay, so this is step 1. Then I repeat the same thing. I take a gradient step of exactly the same step size, okay? It also happens to be pointing, it's got to point towards the center here, but of exactly the same. Then I throw myself on another circle. I may go back, I may not go back, etc., etc. Now, this is Langevin dynamics. Okay? So annealed Langevin dynamics okay, it kind of does the same thing, except it shrinks the step size and the circle radius after every step. Okay, so let's draw one more step here. So then let's say I do this thing again and I happen to land backwards, I don't know, somewhere here. Then I would take another gradient step of the same size but pointing towards my high value. Then I throw myself on another circle here. Okay, etc., etc. I eventually kind of make my way, right, in this noisy style. We can actually draw this picture in 2D, which is not a bad idea for a separate stream. And ... Okay, annealed Langevin dynamics would say something like, hey, I'm here. Okay, I throw myself on the circle. Then I'm gonna take a slightly smaller step And I'm gonna throw myself on a smaller circle. Oh, actually I can do these two together then, good. Oops. Okay, so then I would maybe land, I don't know, here. Then we go again, even smaller step. Actually, why does it tie this? I don't want to tie it. And even smaller circle. And maybe I land somewhere else, etc., etc. Now here's the trick. If in a way this is noisier but faster, it's less noisier but can risk becoming too slow, right? You can see because these circles will shrink. At some point I'm going to take steps so small that I'll just crawl my way to the maximum, right? And so the goal is maximize, i.e. get to darker shades of green. So this is why you can, but then if I pick my exponential rate and my initial step size in a smart way, you can also see that maybe it is better to do the annealed version because I sort of laser down towards the end. Hey, thanks for joining, thanks for chatting. We're just getting started here. But yeah, this is pretty much how our paper used to work. We used to do annealed Langevin dynamics on this surface. Do I know which one? The one by Chip Huyen, or which one? But I've heard about it, but I don't think I've read any ML book. But yeah, we are doing ML, so you joined at the right time. I'm doing diffusion models, but it's still in the kind of basic data science. Okay, I didn't hear. Okay, I don't know about this one. Aurélien Geron. Let me see. I can do a small review. No, okay, I didn't know about this one. Oh, I see, it's with notebooks and everything. Notebooks are available ML3. Okay, this is pretty good. I'm guessing this is geared more towards, yeah, it has everything. Oh, it even has diffusion. Let's see what they have for diffusion models, because I'm doing a diffusion model. I'm working on my diffusion series. So we're working on this basically. Ugh, it's in TensorFlow. This I do not like. We're working in PyTorch. Even this person here is giving a warning, which is really funny. Like, warning, the latest TensorFlows are... Oh, there's a new one in PyTorch. Okay, so I'm looking at... Yeah, that makes sense. But yeah, we're doing... let's see what they have for diffusion. I think I'm explaining... I wonder if he explains it the way I just did then. Oh, there is no, wait a second, there is, oh, I see, there is a denoising diffusion. Oh no, it's a denoising autoencoder. Yeah, from what yeah, TensorFlow is, actually that's funny because I was reading something about this on Reddit. I don't think TensorFlow is gonna make it. We use PyTorch, I use PyTorch at work. And then Triton is also the lower level version. Which goes pretty well hand in hand with PyTorch, right? So if you really want to, because everybody says, oh, TensorFlow is good because it has this TF Lite thing and it has fast inference. But Triton is really the thing, and a bunch of other domain-specific languages that NVIDIA is pushing hard, and OpenAI. How long do you think it would take for beginner to? I think it's what depends what your background is. If it's a beginner with engineering degree or without, or if you have coding experience. Yeah, with engineering it's not too bad, to be honest. Then if you already have like an undergrad or are an undergrad, 1 semester should be fine for for you to get basic ML and to implement something, well, something even more complicated. Like all that classifier stuff is pretty easy. And then, yeah, if you want to get to transformers or diffusion models, the more complicated stuff. Okay, so what I'm actually doing in this series is I don't know if it's the first time watching, but I'm re-implementing one of my grad school papers that I did during my PhD. And we kind of did the basic data science part. Okay, so now we know how to sample from the diffusion model. Yeah, go ahead. I'll just keep, you can ask, you can type anything, don't worry about it. So we know how to sample. Now let's go to our code, because the code itself, we have the training. So then obviously we're gonna need a sampling file. We just have to implement, no, I don't think so. I only did ML in, so when I did, I was the same, I don't know what major you're in, but I was always ECE. And I did like undergrad, masters, and then I started my PhD in like 2017. And then I started ML in like 2019, like 2 years in my PhD, and then I switched completely. So I think it's fine as long as you have the math background. Because I used to do like signal processing for undergrad. I didn't even know about deep learning. Could you describe what's the process of writing a paper? Depends. It's the way I like to do it is I always like to do my code and experiments first, so I have all the results. Okay, the writing itself is not too bad if you have so the thing needs to work first, right? Which is kind of what I'm trying to do here. Like, I need to see the performance numbers of, let's say you do a classifier or something. Once you get those numbers, writing is not too hard. You just write around the results. At least that's how I always did my work. Well, this is the thing. It's not that I look for stuff. It's that I always look for stuff to implement. But then, yeah, I only wrote papers. I never wrote papers in undergrad, so I wouldn't worry too much about it. I don't know, maybe these days it's more competitive, but I had my first paper like, I think it was like late masters, and then only after I got into PhD, after you get an advisor and everything, I started actually producing more papers. And then it depends on the advisor too. Okay, so what was I saying here? So okay, so we have the training. We saw this from last time. Now we need some sort of sampling. I think I'm just going to implement my paper then directly, because it's pretty clear. We just talked about this, so we just need to write this. We just need to implement this formula then. So I take my current estimate, I pass it through the model, I multiply with the step size, then I do square root 2 times the step size, times another beta, times the noise power, times fresh sampled noise. And it's a for loop, a double for loop with L and M, and that's it. Okay, this should be pretty clean then, not too hard. So we need torch. And we just need a function. We're gonna have to functionalize this a bit. And let's say call it sample unconditional, because we just want to create synthetic data, okay? Let's say it doesn't take anything and it just returns a tensor. We'll have to figure out what the inputs are, okay? And it returns something. Oh, well, we know what it does, because it takes... let's see then. Yeah, that's a good question. I covered this. If you go to my YouTube channel, I can post my YouTube channel too, or you can find the profile too in Twitch. It blocked you because of dumb, apparently, but I let the message through. You're good. So I kind of covered it before in my YouTube, but generally a diffusion model is, or what's known as a score-based model, it's pretty much a denoiser. It's actually pretty easy to understand. The way it's trained is it takes as input data plus noise, and it's supposed to predict just the noise. So it's kind of like an anti-denoiser, right? And I think noise is easy to understand what it is, right? You see it in images and camera images and whatnot, all that stuff. So a diffusion model is sort of like a reverse denoiser. Instead of predicting the clean image from or the clean sample from data plus noise, although image is the most common case, it just predicts the noise and the negative noise due to a technicality. That's it. We have this training. The bigger problem is, how do I use the diffusion model? And I use it in something called a reverse diffusion chain because I use it to iteratively purify the data, which is actually what I was drawing before. Actually, this is literally the code I was about to write. So you start from pure noise, you pass it through the model, and it predicts a negative noise. So when it starts, it's going to predict itself, the input, but I multiply with the coefficient. So I add it with the input. So I take some of the noise away, and then I inject a smaller amount back. And then I repeat this. But magically, this somehow uncovers data structure, right? Even if you start from pure noise, the model is biased towards predicting the noise that lies on top of structure. And that's pretty much it. If I repeat this ... which is exactly what I was about to code right now. Let's see. So what do we need to produce data from noise? Well, we need a number of steps. Okay, so we need a number of steps outer, which is an integer, and a number of steps inner, which is an integer. And of course we need the model, I forgot, right? So we need a model, which is a torch.nn.module. Okay, so then the logic would be something like for outer step, for each outer step, then for each inner step, steps inner. I actually have to do exactly what I said. So predict with diffusion model. Okay, so I get output equals model current. Okay, so now what did we say? Unburdens data science for ML. Do I really need to learn deep? Not really. I would start with PyTorch. And so I would recommend Torch. Like for example, Torch supersedes NumPy. PyTorch is basically NumPy, except you can always run it on GPU. So that's for one. Seaborn then is just for plotting nice figures. Again, not Matplotlib these days is okay. I wouldn't bother. Pandas is for data frames. I also don't really use those. So yeah, I would do PyTorch. I would recommend starting with, basic operations. In fact, learning to which one, pandas. Maybe it is, but I've never used it that much myself. Yeah, I'm not too familiar with it. To be honest, I don't even know the basics of data frames. That's a good question. I don't know. Yeah. It's kind of like a beginner guide, but then it almost feels like almost too beginner, to be honest. Like, I would really just look at understanding PyTorch and how to run stuff on GPUs. I think that's a more valuable skill. Like even just figuring out linear algebra operations and random sampling and all that stuff. Which is, by the way, I'm actually just, this is pure PyTorch what I'm writing right now, right? Because I just started from import torch. Okay, so we need, so we have the outer steps, the inner steps, and we pass the model. We're also gonna sample some noise, okay, with the same shape as the output. So I have torch, rand, and like. I don't have to worry about anything else. Then I'm just gonna apply the equation in my paper at the high level, which is I take the current plus the step times the output plus square root of 2 times another beta times the step times the noise power times the noise. Okay, let's see if we memorize that. So apply update step, update equation. This is the core, right? So we have that current becomes current plus step size times output plus square root of 2 times beta times step size times noise power, no, times noise standard deviation times noise. Okay, that's it. So now we just have to figure out the coefficients. So we know that the step size changes every outer step and it becomes alpha 0 times r to the power outer step. This is for geometrical progression, okay? Beta is beta, it's just a number. The noise standard deviation is, I have to take this from the outside because it's the noise levels the diffusion model was trained on at outer step, okay? So now I know more stuff about what I need my input to look like. So I'm also, let me run a, so git add src. By the way, this is all on my GitHub too. If you, I think the link is also on the Twitch or on the YouTube channel. Okay, do we have nicer formatting here? Okay, so what other inputs do I need? I definitely need alpha 0, which is a float. That's it. I need beta, which is another float. That's it. I need r, which is also a float. That's it. What is that? I don't know if I have link. Was that supposed to be a link or? And I need the noise levels, which is supposed to be. Let's say it's a list of floats for now. Yeah, I think I have links disabled, sorry. So current plus this plus 2. Now the thing is the model, and then we want to return the current. Yeah, that's something for that has nothing to do with data science, basically. That's just pure PyTorch, that type of thing. So that's why I said like nothing, pandas is not useful there, NumPy is not, Seaborn is not. That's pure PyTorch basically, or distributed PyTorch, most likely, even just from the title. So I know we need to let's see. So I need to start. What do I need to start with? Noise levels. I need to start from the first noise level, right? Torch, rand, n. Oh, I think I need an init here, actually. because I can't guess the shape of this. I don't want to do the shape passing. So I'm just gonna start from init. Initialize process. Step size times input towards square root 2 beta times step size times noise standard deviation, which is just the noise level. I guess this is fine for now. Okay, so we're done. We actually wrote the sampling. So then what we want to do is in the training process, let's see. What if I, from mymo.sampling, import sample unconditional. No, I don't think so. I don't think so, because I work with language models at work, but then off on stream I do, this is obviously not language models, right? It's like applied to wireless channel data. Then I also did images. I mean, once you get the basics of PyTorch, you can pretty much do anything. It shouldn't be a problem. So MIMO sampling sample. So when do we want to sample here? Run some noise data to get loss function. Pass through model, post process back to complex values. Compute the loss function. Update the model. So then we can say sample from the model. Okay, and we can sample, maybe we don't want to sample every time. There we have to do like a sampling cadence or something. Yeah, NLP and CV, I think that's pretty, I gotta tell you, that sounds, I mean, yeah, they're not that split these days. Like even models like Clip, they're from 2011 and it's impossible to understand it without both. Well, actually, the thing is, even with diffusion, like all this nano banana from Google and stuff, is that text or image, or is it both? That's a tricky answer there, because it's most likely both. I don't think pure vision is that popular these days anymore, to be honest. Everything has a text component too, even if it's like multimodal. Also, everything is unified with transformers. So what do you see here? I don't know, because I've never worked at companies that big. I never bothered trying to get into something that big. So what do I want to do here? So no, I want to say verbose. How do we want to call this parameter? Oh, it's loss verbose. Okay, fine. So then we can call it sampling. So every 100 steps yeah, you're welcome. Thanks for stopping by. Feel free to ask or lurk around, or check out my YouTube if you, because I start basically diffusion from scratch if you're interested. And it's neither NLP nor CV. That's the thing. It's on wireless data, which is neither. It's closer to computer vision, but it's like not really, because I go through complex value data and everything. But it doesn't really matter. Once you get the pipeline, it should work for everything. I see. So we do if step config train sampling verbose. Okay, so then we know we want to sample from. So I need to do the init myself here. So random size. do I get the size of the batch? So do I not have the data config? CFG data. Oh, I see it's here. I don't know if you should. Yeah, reading is. I would do the notebooks or exercises or something. Yeah, it depends on your background though. If you have engineering background, you should speed through it. So data CFG, no CFG data dot sample size. The thing is, I need to start with complex value here, right? Yeah. So we're gonna have to do torch complex 64. The problem becomes, okay. Well, actually no, because I can just pass it, okay? So samples, val samples equals, what do we call this? Sample unconditional. And how many batch? Sampling batch. Let's say we sample 4 channels at the same time. So then this becomes sampling batch, no, CFG train dot sampling batch, and I need to unroll this. Okay, so then what do I need to pass here? Come on, show me the thing. Here's a trickery here because I need to pass the model. Where's the model? Oh, it's just model. Okay. Here's the thing though, because I need to do with torch inference mode, because we want to do this without gradients. So we need to pass the model, the init, config sampling, num steps outer, config sampling, num steps inner. Well, actually, let's do it this way then. Let's just define a sampling config, because I don't want to carry these all the way around. So then we need from data classes import data class. You have to read a lot too. I used to read I probably read about 2,000 papers during my PhD, but you get used to it. CFG sampling. Sampling config, okay. Yeah, but the thing is, when I say read, it's not really read. It's not what you get used to, like speed reading and stuff. It's not. When I say read, I mean like 30-minute session per paper. So then you can do like 4 per day pretty easily, and then the days just add up. I mean, it's over 5 years, right? So it's a ton of time too. Yeah, so then this only needs to take a config. So then it has num steps outer missing, num steps inner int 1, alpha 0. We have to figure out what this is. This is gonna be bad. Missing our float missing. Oh no, beta float should be 1 because we said this is neutral, right? This is our own invention. The thing is I need to set alpha and R. And the noise levels are fine. So then I'm gonna have to, I can just pass a CFG here, which is just a sampling config. And then it can be CFG dot. No, config dot. Config dot. Yeah, PhD was okay. Yeah, it was a lot of work. Nothing too special though. Oh, I don't have missing here. Sorry, I forgot. Okay, then I have to leave these untagged. Okay, so the most important sampling parameters are these 3. It depends per university. Yeah, in the US you have to do that. It's a committee and everything. There's no fixed rules though. Okay, so then we have yeah, many times. That's kind of the point, like probably tens of times for me. Well, I don't know if tens, but yeah. Low tens of times, probably like 20 times or something. It's inverse problems. It's the thing you see where they use AI to fill in missing pieces or to unblur images. Like even that stupid stuff you see on CSI on like crime shows when they say like enhance to zoom into an image. That's pretty much done with AI these days, with the diffusion models specifically, like super resolution and all that stuff. Okay, so I need a config sampling too. Now the problem is I'm gathering configs like crazy here. I guess we'll take another one, which is sampling config. The thing is, if I do it like this, I need to specify the sampling. So num steps outer. I need to tell something to this. Okay, so we're gonna have to guess the values here. This is gonna be where it's tricky because from what I remember we had to, and R, I don't remember what R is either. Something like that, yeah. Except it kind of actually works these days, like with face de-blurring and all that stuff. And there's a lot of math behind it, which is basically my paper and what I'm trying to implement here, which is basically how diffusion models work, because they purify noise iteratively. So you can start with something that's corrupted and get something cleaner, and then repeat it at a micro scale. Steps out or alpha 0 R. So what do I do here? Okay, I have the learning rate. Then I also need, where the heck do I sample? Oh, so I just need to plot these then, right? Yes. And what's the last missing parameter I need? Oh shit, the noise levels. Yeah, this is the critical one. So what am I training the model on? So the thing, I need to, what am I training the noise? Okay, so we need a strong primitive then, because we need a so add noise to data. With what standard deviation? Oh, here it is. Okay. So pick a noise level at random. Yeah, so I need to instantiate noise levels. So here it ties into the R and everything. Okay, gotcha. So there is an R float here, which is 099. Okay, I know what's happening here. So it's like max noise level float. Let's say it's 10.0 R, and the number of noise levels, integer. Let's say it's 1,000. So that means I train on all the way from 10 to 10 times 0.99 to the power of 1,000. Yeah, this seems about right. Okay. Okay, so then given these three, this is enough info. And now the R here becomes, it has to be tied. What do you mean? What are you talking? What are you referring to? If you try to paste the link, it's not gonna work. So it ties into the R here. Yeah, because I need to use exactly the same noise levels. Okay, so the number of steps is also given. Config train. Let's just set this to num noise levels. Okay, this is looking a lot better now. Okay, let me finish this. I'll look at what that is. If it's a GitHub link. There's a lot of work on inference problems though, like hundreds probably. On image reconstruction, all that stuff. Actually, I can do this in post-init then. Because I know... Nah, I shouldn't do this. No. So noise levels should be... it should be to model device. No, to model.device. What should it be? Can I do an easy geometric progression in Torch? So Torch tensor max config train. How can I do this easily? Import Torch. Okay, it's taking a while because why? It's finding my GPU or something. Okay, let me see what this... Actually, I'm not sure what's happening here. Huh. Okay, I guess it was loading the Python image. Yeah, no, it's not like that. That has nothing to do with inverse problems. No, that's just the basic MNIST thing, something somebody did for fun. Diffusion is a bit more complicated. Again, it's on the YouTube series, but yeah. I'm not quite sure what's happening in this repo, but it's like something somebody did for fun, probably. So let's see. So if I start, can I do this? Torch tensor 2 times torch range 10. Oh. Is it A range? Okay, so I can't do a progression. So then I can do times torch tensor 0.99 to the power of. Yeah, I can do. Okay, so it's pretty easy then. So it's the max noise level times well, actually I don't even need to do this. It's times yeah, we're not doing classification. This is reconstruction. It's something, it's a bit different because you start from measurements. So which one? Oh, it's the base R. Config train.r to the power of torch A range config train dot yeah, there's a lot of stuff, but yeah, again, I wouldn't go. Yeah, there's a lot of stuff. I don't think you need to know everything. I would recommend, again, just understanding PyTorch and how to implement these things. The application is not that important. Oh, is it num steps? Yeah, it's the nums. No, it's not num steps. It's num noise levels. Okay, well, this looks pretty bad. Let's see. Can I get it to pre-commit run all? Yes, I can get it nicer. Okay, so we take the max noise level times to do. Okay, so now here it is. The standard deviation becomes so pick noise levels at random. So now we have to pick a random noise level for each sample. So it becomes is there a torch rand choice? Let's see. Torch random choice with replacement. Can I pick multinomial? Do I have to do? Each row contains num sample from multinomial. Multivariate replacement true. So then if I do what was this? Torch multinomial. It's the first time I see this one. So I pick a multinomial from my noise levels and I pick how many samples? The batch. Okay, length of batch. And replacement true. Okay. And val samples, okay. So now I pass all, and then for inference I pass all the noise levels and then they just descend on it, right? So for outer steps, there is a trickery here because I need to check if there's a mismatch between number of outer steps and noise levels. The code is gonna silently error here if I, damn it. So if config num out steps outer is not equal to the length of noise levels, I have to raise runtime error. Unequally spaced sampling not yet supported, right? Because I don't know how we'll do it otherwise. Yeah. Well, this is the whole thing of sampling faster. Okay. So then, now that I have these, sampling batch. Okay, let's see if this runs then. So I should do uv run -m mymo.train. Okay, so we can train like this. Okay, this seems we made it here. So standard deviations, what did I pick? No, because why? Oh, I see. These are just standard deviation IDX, and then I just need to pick. Is it really multinomial gives me just indices then? Eek. Noise levels, standard deviation, IDX. Interesting. It actually gives me. So what is length of noise levels? Multinomial. Yeah, it's indices. Yeah. It's a multinomial referred to class from of tensor. The corresponding distribution located in the corresponding row of tensor. The rows do not. Oh no, wait, I need to make these equal then. It's not noise levels. So how do I pick these? Uniformly at random, right? So then I just do torch dot ones like noise levels. Because I need it to be one everywhere. Oh, I know what's happening here because I'm biasing it towards earlier. That's, of course, okay. Good, so we figured something out because, so now this will give me, with equal probability, it should give me indices scattered. Suspiciously small indices. Really? No. Why am I sampling so low then? Oh, is it because I didn't save? I always do this. Okay, sorry. Standard deviation index. Okay, this looks more like it. Okay, so yeah, now we pick indices. So this is just a fancy sampler with replacement. Okay, we have the standard deviation now. We added the model. There's a time step angle here, which we need to fix too, but we'll fix that next time. And that's it. Then we pass the noise. Let's see if we get this. We can add a TQDM bar here so we know where we are. TQDM, import TQDM. And we can do a range here. Okay, so we can just, let's see if the sampling works. It should be all tied in now. So we implemented sampling. We also fixed the, I see, I need a time step. Okay, yep, there we go. So let's For now, let's assume time step is 1, but we'll fix that next time because we trained with this mysterious variable called time step at 1, 2, which is fine. Somewhere I am missing a... Where am I missing? Something is on... Not on the model device. Oh, in the sampling, okay. Model. Oh, really? What, the current is in it? Did I not place init on the GPU? I did not, of course, obviously. So device is model.device. There we go, that's it. Let's clean this up again. Okay, so now we should be able to run sampling and the bar should show up and the model will work. Aha, I forgot something very important. I need to convert it to reals, okay? So then we'll say val samples. We need to convert this back to complex. Here's the, we did this, we have this, right? We have them in data. Complex to real and real to complex. So I need to do complex to real of the init. Okay. And then the samples is I go back real to complex from the samples. Okay. Again, very close now. Because we can't, deep neural networks don't work with complex value data. What is the model output? It's output sample, okay, because we have this UNet. So it's actually not, there is a trickery here because we need to unpack the output here, which is not the greatest thing. I guess we're stuck with Hugging Face, right? Because this is their convention, yeah. So what, he wants me to do everything with tensors? I cannot even put torch square root step size. Argument input. Torch square root doesn't work on tensors? Okay, so we can just magically declare all this as the noise standard deviation times that, and we'll just do it like this. And this should actually clean up that line. The only problem is I have to convert these two. And I really don't want to do this actually. Can we tensorize all the config? It really feels like we should, right? So we don't want to move data. Okay, we'll do it. This is not too good though, because you have to move it to the device. And then this is it, okay. But yeah, we have to tensorize beta too on the device, and I'm pretty sure this is not good because we keep moving these tiny scalars around. That doesn't sound good. I mean, it sounds slow. Okay, there we go. So we're actually sampling now. Okay, that's it. So we're producing synthetic data. Now, how we evaluate this, it's actually this is harder even than the paper itself, because there is no way to evaluate these without domain expertise. And for wireless channels, there are certain metrics you can look at, but it's very hard to tell if these samples are real. But what we can do is we can plot and save them. And we'll do that next time, okay? So for now, yeah, at least we're able to fully generate synthetic data. And we can just check the tensor shape is right, but it should be 4 complex valued channels. And we're very close. We actually wrote sample unconditional, which is we basically implemented 2/3 of the equation from the paper. And that's it. There's another basically conditional term, which will come here, plus some ... plus something. And then we have the paper. So that will be the function called sample conditional. And we have to do some other things with inverse problems, which we'll talk about next time. But yeah, our channels are ready, and there we go. They have the right shape. They're complex valued matrices. The magnitude looks about okay, actually. So it's in the range. And so we'll see what we do with these next time if you're watching on YouTube. So that's it for this part. All right, we can cut there, and let's push this to GitHub. What did we change in CDL? Oh, nothing relevant. I just messed around with it. Yeah, okay. Don't care about that one. CDL. Yeah, we added sampling, and we changed the training such that it samples. Git commit, add unconditional sampling. Whoops. Okay. Let me move this branch to a better name because it should be unconditional sampling. There we go. And we can push this. So now it's public. Okay, and then I'm gonna take a break, and after the break is let's figure out what the plan should be after the break. So what else can we do? We can so we have unconditional sampling. We're gonna have to plot these to visualize, but that's not the most important thing. Compute the loss function. We're training the score model. This I don't like. I'm gonna cut all this stuff. That doc string is way too large. Noise. Is this complex valued noise? Yeah, it is complex valued noise. With that standard deviation divided by the coefficient. So we can plot these and the samples should look better. So now we also have the geometrical progression implemented, which is pretty big. So we'll have to tune these. Yeah, I think next time we should do the inverse problem then, or the conditional sampling, right? Because we did sample unconditional. We're very close to finishing the paper, basically. It starts from init. We can't support the irregular steps yet. That's fine. What else do we need here? Not too much. We have the step size, noise standard deviation. This is basically the algorithm from our paper. 2 times beta times the step size, and the noise levels, they also decrease with the outer step. And that's it. We take the output, we generate fresh noise, and we do the update, which is current plus the output, and then the output itself is the estimated negative noise, because I do the loss is the model prediction plus the noise, so it learns to minimize the loss, so negative noise. Okay, so yeah, next time we have to explain what an inverse problem is. So I'll be back after a 2-minute break. It's gonna be pretty interesting though, because it's basically how those in-painting models work, the big ones, which is pretty tricky. Okay, so yeah, we'll revisit the unconditional sampling. So maybe we should warp that loss surface a bit. Yeah. Okay, well, I'll be back after a break. All right, we're back with more coding. More of the series where I reproduce my grad school paper, and let's just get back into it and let's see where we left off last time, which I think it was we did unconditional sampling, right? So if we check the diagram, yeah, we sort of recapped how the Neil-Langevin dynamics works for unconditional sampling, where we just want to produce data from noise. And another nice picture is that something like this, where a darker shade of green means a more realistic looking image, and lighter shade is a more noisy or noise-like or less structured image. So then first we have Langevin dynamics, which sort of takes an equal step size, well, proportional to the gradient too, but assuming the gradient is equal everywhere here, which is maybe not the best drawing. But then the Neil-Langevin dynamics sort of shrinks the step size and the added noise, because after every time we take a step, we also add some noise back to throw us in a sort of a circle or a hypersphere. So that pretty much implements our paper, except for the conditional part. We also need some measurements, and we want this sample to satisfy another condition, okay? So the most basic way to view it is if we take this and we turn this into conditional inference or conditional sampling, still with the Neil-Langevin dynamics, okay? We're gonna add yet another term here, okay? To the three-way sum. It's now going to be a four-way sum, and the fourth term that gets added will be something that in words measures how close the current sample is. No, let's do it this way. How consistent the current sample is with the observations. Okay? So then what happens is we have this concept of observations, which are always the same. So in an inverse problem, we're given some observations which are fixed, okay? We're just given these observations, and they never change across. They don't depend on the sampling process, so it should not be confused. Let's mark them like this, okay? And these observations, they give us, if I input the current sample, okay, so then we can call this a consistency loss, consistency term, okay? Let's call it a consistency update, even better, because it updates, right? And what this does is it takes as input the current sample, we just said that, right? And it also takes as input the observations, which are always the same. So I'm going to drag them from here, the same observations. And this box measures how consistent. It doesn't measure though, it updates the current sample to be more consistent with observations, okay? And that's pretty much it. So then this repeats now. Nothing else changes, right? This is still iterative. Now we're gonna have another consistency update at the second step. I'm gonna have to make these larger, but it's the same formula, except this one now sees the new estimate, right? Oh, this is kind of crooked. Let's fix it. There we go. So now this guy again goes to its consistency update. The observations are the same, so they go in here. And this consistency update again informs the entire sum. And this repeats, okay? And now this is also multiplied with the same coefficient, okay? So it's also times AR, actually, here. Like this. And it's times AR squared here, and so on and so forth. So the formula we have is very, very close to this. We just got to implement this consistency part, all right? So that's all we have to do. We have to implement the we have to implement the consistency update, and it's some sort of function that takes the current sample and the observations, and we should say and forward process and observation measurement process. Okay, so this sounds a bit abstract because that's kind of how I wanted to do it. But generically, the difference between conditional sampling and unconditional sampling is I want to produce data that is realistic, but also satisfies another criterion. In this, and we call it the observations because that's what happens in real life, right? You observe something else from the environment, and you want to recreate the data that creates those observations. So that's an inverse problem, okay? So this is why it's called inverse problem, right? Because in nature, we have a underlying, let's call it signal, or okay, so we have an underlying signal and it produces observations. Okay, whoops. And the act of going from the signal to the observations, in inverse problem world, this is called a forward process. The reverse is an inverse problem. Given observations, can you guess what produced them? Okay? So this has a ton of real world applications, right? You can think of, I don't know, weather applications or something like that. Given that I observe a certain weather phenomenon, what was the temperature in a certain location? Now, there's also a causality here, right? Like who causes who. But generally in processes or in things that happen in nature where it is clear that we're just observing a part or an effect of a signal and we want to guess the underlying signal. And now here comes the application that everybody knows. It's when you do image super resolution, right? So I have a blurry, low quality image, and I want to get the clean image. Well, if I have a clean image, producing a blurry one is really easy, okay? So it's easy to destroy things, okay? So the forward process will be blurring, okay? Easy. With a blurring matrix, e.g., let's call this y equals ax, okay? Or let's actually, or we can say conv, right? It's the convolution between a kernel, and my original image x, okay? So then let's call the original, the clean image x, and we can call the measurements or the observation y. The problem is going in reverse is an inverse problem. Okay, and this is what you would call de-blurring. Or super resolution is something else. It's kind of when you change the resolution, but there's also denoising itself is an inverse problem. Okay, if I have an image, so let's do that one, right? So another example of an inverse problem is X, and I have a noisy image of the same shape. Okay, so noising, easy. It's just Y equals A plus N, or let's say sigma times N, right, with some power. Denoising is not that easy. There's classical tools. The same goes for deblurring. There's classical tools to do it. There's AI tools to do it. And another one that's popular is in painting, right? So I observe image with missing pixels, okay? So let's say somebody censors it in a way that I just have like all zeros here. So I have a hole in my image. Can I guess what was here? Okay, so this is called in painting, which is Y is A times X now. This is still a linear operation, right? I'm just gonna multiply. We can think of this as pointwise multiply. Sorry. So it's just a process where I multiply each pixel with either 1 or 0, and then I have some missing. They don't even have to be contiguous, right? I can miss a chunk here, and another chunk here, and a small chunk here, okay? So the process is, the reverse process is called in painting, because I want to paint inside the missing ones. This is just called masking, okay? The forward process. The inverse problem, or the reverse process, is in painting, okay? Which is much harder, again. So now maybe we understand why we explained it this way. Let's go back to our conditional sampling with generative models. Because if we look at the diffusion update, it helps us, the unconditional one helps us generate a realistic looking signal just from pure noise. And now I add this term which encourages the signal to behave consistently with the measurements, okay, with the observations. And if I know that measurement process and the observations, I can analytically write a function that tells me how close is the signal to my measurements if I were to measure it again, okay? So let's distill this picture to be even more intuitive then, right? So what does this tell us? This tells us that I start, okay, so start from an initial guess. Then I regenerate the measurements from it. This is easy, right? Because destroying is easy. Okay, so we know how to generate measurements because that's the forward process. And then I compare them with with real observations by using, e.g., sum of differences, sum of absolute or mean squared error, and update my guess with the gradient from this error term. And that's it, right? These are the 4 steps that give us the refined guess. And this is just the data, the inverse problem part of it, right? So what do we do here? So we take the initial guess, okay? We regenerate the measurements from it, which again, this is easy because destroying is easy with the forward process. We also have the observations, the real ones, and they're always the same, okay? And we're just going to compare the regenerated observations with the real ones. This gives us a term, which gives us a gradient direction, which allows us to update our refined guess. And this is how, and we usually, the update process involves the initial guess and updating it with something additive, for example, or moving it into a certain direction. And that's it, right? So we can say that these are the measurements, and then this is the update process, and this is sort of this diagonal box here expanded, okay? And everything else we talked about in diffusion sampling stays the same, but this kind of makes sense. So let's go to the examples now, right? So for example, if I have blurred measurements of an image and I have a guess from the image, how am I going to measure if the guess is right? I'm going to take the guess, I'm going to re-blur it, and I'm going to compare the blurred versions, right? So another way to put it is that I'm going to take X and I'm going to form a Y regen, okay, which is another blurry low quality image. And then I just compare these two, and this gives me the update term, okay? The same goes for noising, okay? If I know that my measurements are noisy images, and I have something that I think is the clean image, how am I gonna tell if it's really consistent with the measurements? I'm gonna take the clean image and add noise back to it, okay? The same goes for masking, and think carefully, it's trickier here, okay? So let's say that I know that I observed only some pixels from an image, and now I have a guess for the entire image, including where I didn't see the pixels. How can I tell if it's consistent with the measurements? Well, I'm gonna remask it and basically delete those pixels and only compare it, right? So I'm gonna produce this thing here. Hey, thanks for joining. Thanks for joining the stream on YouTube. I am on YouTube too, yes. So we have we have this image with missing pixels, the observations, we have a guess for it. How am I going to compare it? Well, we're going to regenerate by remasking, okay? So this process becomes remasking, or just masking. We can just call it masking. And this makes sense because this is the only way we can coherently guess if something is consistent, right? Because if I have some observations, I'm just gonna regenerate the observations, and that's it. So we're gonna have to implement this in math, but then it's not that hard, right? Because masking is still y equals ax. So then the loss here, for example, just becomes y minus ax current. Okay, and then what did I say we do? We do the squared norm and we get the gradient of this. Okay, so this is actually what we do in our paper. That Brownian ocean is related to the, yes, it is. That's exactly the noisy, the denoising part, right? Because let's say I have some noisy observations and I have a guess for them. To compare how close I am, I'm just going to add some noise back and then I'm going to denoise. And actually, I'm going to do this repeatedly, but with reduced noise levels every time if I couple it with the diffusion sampling. And ultimately, the whole thing converges. So I went through this, well, actually, I went through this earlier in the stream, but it'll be up on YouTube too. So now, going back is we need to understand one thing about wireless channels though, okay? So the fundamental question then becomes, what is the measurement process for wireless channels? Well, it's pretty easy, okay? So measurements in wireless channels. I'm just gonna write it algebraically, but well, maybe not. The idea is we start from the wireless channel, the complete wireless channel, and we measure it using pilot signals, so pilot measurements, okay? The way this works is like if you it's kind of like the multi-speaker thing, where imagine you listen to two people at the same time, and then you want to understand how their signals are interleaved. The information that you have is that you know what they spoke, okay, what each of them spoke. So then you have to recreate the channel from the mixed signal, right? So then this is called pilots, and then the inverse problem is called channel estimation, which is finally, now we understand the title of the paper that we're trying to re-implement, right? MIMO channel estimation. And that's it. So let's do it. Yeah, I work in ML. Thanks for the question. Yeah, I'm pretty close, like an applied ML engineer, or some, you can call it that. Yeah, exactly. This is it's an inverse. I'm just trying to do an inverse problem with the diffusion model. So, okay, so let's see how the coding is gonna go. Last time we implemented the unconditional sampling, which is without any observations, right? So it's really not too hard. Maybe we can generalize this function. Maybe we don't even need to write another function. What if we just magically call this sample from model, and we just give it measurements, which is either a torch tensor or none. And then if this is none, then we won't apply the measurement term. And that's it. Then we'll write the equation as it is, okay? So then we have the apply the unconditional update equation, and then all we need to do is apply conditional update equation. So now the forward process in MIMO channels is pretty easy. It's a matrix multiplication between the pilot matrix and the channel. So then we can say if measurements, if they're not none, then we can say conditional, okay, becomes the step size. It has exactly the same, well, we have to look in the paper now. Yes, this is yes, it is similar to a Kalman filter, because there is a loop here and you iteratively filter. Yes, so that's a good point. Diffusion models are pretty much denoisers, and we're doing iterative denoising, but also with the data term here. Yes, it's an annealed, yeah, it's also an annealed process, because we shrink the, I don't remember if this is what they do in Kalman filtering too, if they shrink the added noise power back into the process at every step, but there is also an exponential shrinkage here, because this config R is raised to the power and it's a subunitary number. So yeah, this is signal processing, obviously, except it's done with also info from a deep neural network. So we need to apply the conditional update equation. So we have the same step size, and now I have to look in the paper because I don't really remember what it is. Okay, so here it is, same step size. So I take the current estimate, I matrix multiply with P. So I need also the pilot matrix if I have the measurement, I forgot. And then I multiply with the transpose and complex conjugate P. And I divide. I also need to know information about the noise power that is added in the measurement process. because in wireless channels you not only measure with matrix, actually we know this, we already implemented this in the first episode, but this is the forward process, right? It's pretty easy. You just take the matrix H, right, multiply it with the P, and you add noise with a certain power. So then I need to know the P, the Y are the measurements, I have them. I need to also know the P. I also need to know the N. And yes, we are using annealing here too, because we're decreasing the step size. And sigma, I also need to take into account the noise that I add in the process. Okay, let's see, can we memorize this? H times P minus Y, and okay, I think we can. And I need to flip the sign here, because I want to descend in this direction. Metropolis, that's something for, I think that's a randomly, that's something to do with randomly choosing to add noise or not, right? Here we determine it, we add it every step, and also we stop after a fixed number of steps. So it's actually it's probably simpler than that. Like the stopping criterion is fixed here. We just run this process for a number of steps. Okay, so I need to know P also, so let's go back here. So then we also need pilots, which is also, we either have it or not. And we need measurement, noise, standard deviation, which is either a float or we don't have it. So if we have the measurements, this will be negative because we want to take a step in the, well, no, let's leave it positive. We'll update it. And then our current will be current minus conditional. Well, actually, let's do it this way. Step size times conditional. Let's compute the conditional term purely by itself. So what did we say it is? It's torch matmul. I take my current. I multiply with the pilots. I subtract the measurements. And I multiply the whole thing with the complex conjugate pilots. Dot conj dot, I need to do I have dot Hermitian in PyTorch? That would be nice. Oh, PyTorch doesn't have complex Hermitian? Not even in the last version I'm on? PyTorch complex Hermitian or it doesn't have the H? T, does T work for, so T works on complexes, does it also conjugate, or I have to do .t.conj? Also, I need this to work on, okay, so let's just mess around with it, it's probably faster. Because this is also in the batch operation. So if I have, so let's say I have X, torch, rand, n, 4, 4, 6, D type, torch, complex 64. If I do .t, what does this do? X.t.shape. It's not good because it flips everything, right? No, I just need to flip the last two. I believe it's X.transpose -1 -2. Yeah, so I need to permute the last two axes and also do conj. Because there is a difference between, yeah, okay, so there is, I'm surprised there's no there's no Hermitian. Interesting. I thought they would have it by now. But in any case, we know it's the last two axes. So what do we say we do? Pilot.transpose -1 -2 .conj. Okay, so we multiply this. Where's the matmul? Here. matmul. Oh, this, comma, okay. And I have to divide by measurement noise. Is it deviation or power? I think it's power. I think these are all squared. All right, squared plus, let me clean this up a bit because it looks ugly, sorry. Oh, actually, I cannot clean this up. Okay, never mind. So it's times measurement. Is it? I think it's got to be powers, right? Yeah, it's squared. Okay. So then I also take the current noise standard deviation and I square that too. Okay. So then let me see if this cleans up. Okay, it does clean up. Okay, there we go. So matmul h times p minus y times p Hermitian divided by squared measurement noise plus noise standard deviation. And yeah, you're right. So we can do a safety check here. If not, pilots and measurement noise raise runtime error. Pilots and measurement noise must be passed together with measurements. Okay, so we know that we don't do division by nones. And that's it. So this is directly the gradient term, right? So actually we can maybe separate this again. So let's see. Reconstructed measurements will be, well, it's just torch matmul then, okay? And then this, the gradient is just the difference then. Difference multiplied by the pilots divided. Okay, this is as clean as we'll probably get it. And that's it. We take a step. We want to decrease this. And then the rest remains the same. This output is given by the model. It pushes the signal to a more likely direction, but in pure, like just natural signal space. Okay, so then we're done here. So let's go back to training now. So let's also, so before we used to sample from the model, unconditional. Let's also sample conditional now, right? So we can say sample. Oh wait, we have to, what did we change here? Oh, it's just called sample from model, okay. We have to do something with these. Plot the samples, and we also sample conditional. Now to sample conditional, we need to generate the measurements in the first place, and the pilots. So now we can do this here. Yes, it is. Yep, it is likelihood. Except the likelihood comes from a deep neural network because it's not for image. It's for wireless channels, which are like they sort of look. They're still 2D signals, but they're complex valued. So they look like an environment, and the axes are receiver and transmitter number of antennas. Exactly. So the diffusion model just learns the natural distribution, and then the conditional term pushes it to be consistent with the measurements. But it is very close to image deblurring or whatever, because like wireless channel estimation is basically image estimation. So that is true. So then, okay, so first we need to generate pilots. So now, if I remember correctly, the pilots in wireless channels are pretty basic. They are just 1 over square root of 2 random plus minus 1 real and imaginary part. Let's see, how do we code this? I can take sine of torch rand like. I think this is the closest one, right? So, but for this I need a parameter that tells me the number of pilots. So So actually we need another config here. Oh my god, okay, we have way too many configs, but it's better to keep them separated. So I need a measurement config. And let's use an undersampling factor, because we always want to test this when we have fewer pilots than receive antennas, because otherwise it's too easy of a problem, because you would have more measurements than the real signal. Which that's also technically an inverse problem, but it's like a much easier one. So what do we need here? Let's call it an undersampling, which is a float, and we'll put it to 0.5, half by default. I think that's it. That's all we need, because we know the pilots are always plus minus 1. So then it's just a matter of picking the right. Okay, this is not worth a config then. Hang on, where do we put this? In data? Yes, it should live in data. So undersampling, float. Okay, because we know the image size, the channel matrix size is 1664, but we're only going to observe 8 times 64 because we undersampled the... No, sorry, 16 times 32, because we do right multiply, right? So then the pilot matrix in this case will be 6432. And then when we multiply with 1664, it gives us a 1632 measurement. And our job is to estimate the channel, which is higher dimensional, from this. Okay, so this controls the... So then we need the pilot matrix to be number of transmitters times this factor. Yeah. Okay, so then we have CFG, what is it called? Data CFG dot undersampling. Okay, so then we can just look at, we don't need this now. So first we need to generate the pilot matrix, which will be 6432. So, it's a rand n. I'm just gonna take it signed though. This is the cheap way to do it. Plus another rand n with a sign. Yeah, but so the left dimension of this is always the second dimension of the image, because that multiply has to work. Now, hang on, we have to do this per batch too. Why don't I do this actually? Why don't we do it the cheap way? So I'm just gonna build a full matrix. No, it doesn't work, hang on. Okay, so the batch will be the same, okay? The other dimension is the last one, and the third dimension is the last one times the coefficient. Except we need to take an integer here. We need to round it. So CFG data dot, what do we call this? Undersampling. Except I also need to do an int here. Because I don't know if it rounds. I don't think it works there. What if the dimension is odd sized? Because I need integers. It's better to use the fixed number when we know we have it, and then just only multiply down, not up. Okay, so then it'll be, because I know this is always 0, this is always -1, and then the third dimension of the pilot is the one that changes, and it's -1 times data undersampling, and it's the same for the imaginary part. Okay, and I think that's it. Now this does look pretty ugly, so let's split this into 2 then. Pilot's real is just this, and pilots imaginary is also exactly just this. And then pilots is just, I don't even need all this. It's just 1 over torch square root of 2 times pilots real plus 1j times pilots imaginary. Now I also do take the sign here because I only care about plus minus 1. Okay, this looks a bit cleaner now. Okay, so we have the pilots. Then we can generate the measurements. Now it's trivial, right? It's just torch, matmul, val samples, pilots, done. Plus the noise. Forgot about the noise. So we also need in data measurement noise, which is also a float, and let's put it to something small, standard deviation convention. Okay, so then we're going to do plus data config times config data dot measurement noise times torch rand n like. This is another case where I need to split. So clean measurements, I'm first gonna get these, and then the noise is just, the measurements are just measurement clean plus torch rand n like clean. Okay, and we're gonna call these noisy measurements. And I'm gonna call these clean y because the names are too long and I kind of don't like it. Okay, there we go. This is pretty clean now. So now I have all the 3 things I need because I have the okay, so then I can just run conditional sampling, which is exactly this. Now there is a lot of trickery here. I made a mistake because neural networks, they work with complex values, with real values. They don't work with complex values. So actually in unconditional sampling, I can stay in real world, but here I cannot. I have to be careful because this current is real valued. So what I actually have to do is I have to convert this back to complex, but I have a utility for it. So from mimo.data import complex to real and real to complex. So when we do this matrix multiply, I have to go back to complex world. Let's keep the pilots in complex world because it's easier. Complex world, we'll keep the measurements in complex world too. Complex world, complex. Real world. So I need to go complex to real here. Okay. And this should be it. Okay, so now I can go back. So now to sample, I need the last 3 arguments, which are in order, measurements, noisy, pilots, and the standard deviation of the added noise power. Okay, let's do and that's it. Let's see if this runs, and if it does run, we can do the plots. And well, it's not gonna work because we have to train the model, so the plots will look bad in the beginning, but then we can actually track this loss now during training too. So then I just uv run -m mimo.train. We probably missed a few things, but they should be easy to clean up now. Oh, I need to put defaults here. So let's do equals none, so we don't specify them. So it doesn't, so by default these are off. Okay. Okay, it's going. Okay, so first it's doing the unconditional sampling because it's gonna go through 2 progress bars. Now, of course, the model is not trained, so these will look badly. And maybe it's not a good idea. We're waiting too long here. I should have just commented that out, but it's fine. The interesting thing is I wonder if we can get both of them for free. I think we can, because I can just, well, no, we can't, because it's two different trajectories. What am I talking about? No. Yeah, it's not gonna work. So I do have to pay twice the compute if I want to sample conditional and unconditional. Okay, that's pretty much it. So then we have 4 samples. I can just plot them in a 2x2 grid. That should be pretty basic. While this is running, now I want to see it move through the, I hope I didn't make any shape errors here. Let's see. Of course I did. Oh, yeah. Okay, so it's yelling about tensors. I hate this from PyTorch because oh yeah, I forgot I have to do shapes. No, what am I doing here? Sorry, it's all shapes. All right, so this is a big mistake. It's not a matrix. Okay, and let me comment this part out then, so we don't have to wait for it. And try again. Because now it'll go straight to the thing. Now I think I'm gonna get init, I can use init here independently because it's only for shapes. Yes, I can. Oh, but wait, I need validation data. I actually need real validation data. Okay, I'm just gonna do it on init, which is just random Gaussian channels, just to see if the thing works. But that has to be a real channel, so I actually need a fully sampled channel for, sorry. Which we have, because I have the validation data. It's just a matter of only get input must position 1. Also, I can't even do torch. What? I can't even do torch square root of 2? Is this how bad PyTorch is these days? Like, really? Yeah, I guess I can't. Well, this is pretty annoying. Interesting. Then it's cheaper for me to work with NumPy actually, because this works in PyTorch, multiplying a tensor. Also, I forgot to put device here, which will bite me. So device on device. Okay. Device on device. I need to import NumPy. Yeah, no, it's easier with the thing is now you get to the problem with multiplying a number with a tensor, but interestingly enough, that one does work in PyTorch, right? If I do 3.1 times torch randan 1, yeah, this does work. Okay, so at least, okay, so now I have tensor. This is scalar, tensor, scalar, but it's fine because it's multiplied. Randan like takes care of the device. Are the pilots on the right device? They are. Is the init on the right device? It is. Okay, this function should work. Okay, we're much closer now. I think it should run now. Now, meanwhile, we have to actually, interesting. I cannot test tensors for booleans in PyTorch. So I have to explicitly here is not none. And then if pilots is none or measurement noise standard is none, this should work now. These are all PyTorch limitations. They don't allow you to test the Boolean. Okay, there we go. So it's doing something. It's actually sampling. Another big issue, usually which I used to encounter in my paper, was numerical degeneracy with an untrained model, which may give you not a number because the gradient points in wild directions. If the step size is too large, this will likely degenerate numerically, and there's not much we can fix there because it's an untrained network, so the prior is like completely random. It's also random data, like we're testing this, we're basically taking measurements from a random channel. Yes, it is. I'm basically, the YouTube series I'm in right now, this is like the 12th episode. Yeah, this is our paper. Yeah, this is my paper from like 5 years ago. It's been quite a while. But yeah, I did this a while ago. It's one of my, it's both, right? It's my paper, but I also want to clean up the code, so I'm sort of redoing it from scratch. Although the repo, the original repo is, I have some older YouTube episodes. It's not too bad, but it has like a bunch of hard codes. So I'm just redoing it all from scratch. And the idea is that I'm also using modern neural networks from diffusers. Yeah. I stayed in the field. I'm basically a research scientist. I haven't done wireless that much though. It's like everybody does. I have to do language now. Everybody does LLMs, right? So we have to do it. I've kind of been out of wireless and inverse problems. Nah, I wish. I'm out of signal processing. I do language now. I'm forced to work with language models, but it's not too bad. Yeah. All right, so we finished sampling. Now, the only test we can do here is the shape right. It is right because it's the full channel shape, even though we went in with measurements. Oh, let's see, clean noisy y dot shape. Okay, so we went in with half measurements. We got out full things. The only other thing is, yeah, it's not a number. Okay, so we have significant numerical. So the problem now becomes, how do we set the step size? Because it's like way too large probably. But we can, this is not too bad. We have a stable code now, at least it runs. The only thing is we can early exit if we hit not a number. So let's add this code and we can do the early exit trickery because I don't want to spend too much time. So am I in the branch here? Yes, conditional. Condition. First implementation. Yeah, I know. I mean, everything is, if you put it that way, everything is matrix. Yeah, I mean, even the thing is, another thing I want to do is even the models for images these days, they use transformers, right? It's diffusion transformer or vision transformer, obviously time series too. So everybody's yelling for attention, it seems like it. But that's actually one of the things I want to get to eventually. Once we stabilize training, I want to try some transformer architectures. Because back when I did this, transformers were not that popular. But I'm still on a UNet right now from diffusers. Yeah, I want to get to a VIT, yes. Or well, for diffusion, it's called a DIT. It's a diffusion transformer. It has even more specializations. Okay, so now we have we sample the pilots. The only thing we can do to be a bit cheeky is we can say early stop, early exit. We can early exit on the external loop, on the outer loop. Early exit if we encounter NaN, because there's no point anymore. Yeah, we shouldn't continue. So if, I think Torch has is NaN. So if current dot is, really? It has it, right? Yes, it does. Is NaN dot any. If we see even one NaN, we can just return current. We're gonna have to print a warning though. Which reminds me, we have to also use proper logging, which we don't do because we want to log this at warning level. Warning, sampling exited early because of nan values. Interestingly, PyTorch doesn't crash. It lets you put the nan through a deep neural network, but it's like you're literally wasting compute. So we can do it at the, it's okay. These inner steps are, it's just one, so I don't even have them. But then once we hit something, we can early exit. And that's it. This is for conditional sampling. Okay, so next time we can load the validation data or, yeah. So this was it for conditional sampling. Okay. I'm gonna take a quick break and then I'll keep going because this is a good cut for YouTube for uploading, but otherwise I'll keep on going right now. Let's see, let's plan a bit. So I have the data file, I just have to load it. It's actually, where do I load? Oh, here it is, data set. I just need to call this training, and we actually need a proper validation data set. And then we can run inverse. Oh yeah, and we need to plot the samples, I forgot, because we're not going to be able to do anything here. But interestingly, we can, yes, well, here's the funny thing with tomography. My most cited paper, well, we're the group that sort of pioneered that for MRI. Where is it? Robust compressed sensing. Oh, here it is, yeah. I was joint first author on this one. It's exactly the same idea. This one is even closer to imaging, right? It's not CT, but it's MRI, but it's also complex valued. And yeah, it was with diffusion models. At the time, this is even older. It's like we started working on this in 2020, almost 6 years ago. But yeah, this is probably one of my more successful, no, it is my most successful paper. Okay, but then I just took that and I said, okay, let's just do it for MIMO channels because they're basically images anyways. Like it's the same thing, right? Which was a pretty easy reach at the time. All right, let me take a break and yeah, we have that. I remember we used to do, so it's actually one of the baselines. I worked on the baselines. It's L1 wavelet. This is a non-deep learning method. Yeah. Well, if our method is it's kind of what the thing is. We use a deep neural network that's learned, so it's highly non-linear. You can't really express it in closed form other than like. It's not a proper basis function. It's just like the deep neural network directly gives you the gradient. Let me see what is. Yeah, actually, you're probably more advanced than I am because I don't recognize some of these. Yeah. Yeah, it's used for recognition testing, made across the finite element method. Yes, it is actually interesting. I actually never heard of this. It seems you're more advanced than I am in signal processing for sure, or at least okay. I've been out of it for like 5 years too. But see here, they still pick a basis though. With deep neural networks, there's no guarantee that. Oh, it's just some functions. We can use VNSs starting to get the girl for integration. I don't think we can guarantee. Yeah, with deep neural networks, you throw away all these guarantees, right? Unfortunately, like we don't know if the error is orthogonal. It's just we do blind gradient ascent basically. Yeah, now that reminds me, I wonder if somebody does try to guarantee. I've seen that before. Oh, you know what it is? Hang on, you're right. It's MODL. It's some even older work. I think I remember now. I used to work with this So in this paper, they actually enforce the orthogonality here. Yeah, because they take the residual and they apply something here. Yeah, they train on the residual, right? So it's x minus denoised x. And then, yeah, the diffusion model is also a denoiser. It kind of is the same thing, except exactly. So diffusion model gives you directly the gradient of this instead of you having to compute it yourself and back propagating it, either in closed form or through a network. Yeah. So yeah, but interestingly, yeah, now I'm curious if somebody combined this with diffusion, but I haven't read the literature in a while. Okay, well, thanks for sticking around. I'll be back in a few minutes. Gotta take a quick break, then I'll continue with some more coding. All right. All right, we're back. Let's see, before I start, okay, let me check out this, let's see what's happening here. Econometron, never heard about that. Let me hang on, because I didn't mean to close my paper. Econometron. Oh, interesting. For instance, time series models with these. Is it open source? It is open source, right? MIT license. Oh, this is yours. This is the okay. I can tell from your username. Let's see what's happening here. Econometric modeling, multivariate statistical. Okay, so it's on the classical side. Varima, neural network based forecast. Okay, no, it has neural networks too. States-based models. Okay, this is why. This is Bayes simple function responses, nonlinear against type pip install, fitting a VAR model, data model, data max check stationarity, results model fit. Okay, so you went with the scikit-learn interface. Yeah, pretty nice. Econometron, filters. Oh no, it's in models probably, right? What is in state space? Okay, so it works on data frames. I don't really work with pandas. Like I rarely, I don't think I've ever worked. I was always more of a tensor guy. GPU computing. Actually, that's well, it'd be nice if this would. It would be nice if this would run on GPU. Now that I think about it, but I'm guessing it's all CPU, right? Or does SciPy have GPU these days? I don't even know. Handle their parameters. Set priors, so you can inject yourself here. Yeah, I'm checking the code because I usually like stuff that allows me to modify it myself. So this seems to be pretty modular, pretty clean. Yeah, nice job. So you can set the priors, must be a dict. Not self technique. Okay, priors only for Bayes, so it forces you into, well, this is fine because we're doing Bayesian too. Make prior function. Prior function. Brand name is priors. I'm wondering if you can abuse this to sort of have a deep neural network prior dict string tuple. Distribution object is a SciPy stats distribution. Okay, so you have to mimic this one. All right. Well, thanks for pointing this out. So you have a website too. Yeah, looks pretty good. I haven't worked. I've never worked with time series, to be honest. Let's. All right. So let's see. Where did we leave off? Can we get this thing here? All right, so we're back with more coding. Where did we leave off last time? Well, we left off at training, and we actually had injected conditional sampling in the training loop and unconditional. Now the problem is it does take a bit of compute, but it's fine. So the one piece that we're missing is if we do this early, it's gonna crash. But let's, just for fun, no, but we don't want to do this, right? We need to plot the samples. And we should also run estimation. So today let's focus on the data pipeline, because we loaded training data. We don't really have validation data, right? So let's see, what do we have here? Where do we leave off? Right now we just have a thing called data set, which is really train. This should be train data loader, train data set, and train data. Okay, so it should be train data set, train data loader, get data. Now we also need, of course, a validation data. We can't get the same config data though. We have to change one field in it. If I remember correctly, this data config tag. So we need to get this with data tag. Here it is, config data. So what do we do here? We can change this in. This is obviously tagged train val. Data there is the same. Okay, let's just get config data. We'll just make another config here. Val. It's the same directory but with val, and then train is with train, of course, val with val. The problem is I'm kind of hogging the interface here because now I have like 5 configs, which is getting pretty ridiculous. But we can use Pydantic next time, which is pretty nice actually. It's very clean Python. Okay, so now we have config data train and val. Config data train and val. Okay. The model is given by the config data train. That makes sense because the model has to be aware. The train data is given by config data train. The val data is given by config data val. Oh, somebody followed. Thanks for the Twitch follow. Appreciate that. We're just working on diffusion models for inverse problems over here. And we sort of have the full pipeline going. I don't know if you've been watching or not, but it's fine. Thanks for stopping by. Feel free to lurk or ask questions. So I was about to get the val data set. Okay, this is obviously val data. And the val data loader, which is obviously the same thing. Shuffle through, config. Now this one will have a fixed, let's just get 4 samples for validation every time. Of course, to be fair, we also need a config val. Yeah, we're not gonna do that. There's way too many configs already. Val data set. So now what we can do is we can actually pull some real data at validation time. Finally, very good. So let's say validate and sample from the model. Another basic thing though, because this diffusion model is kind of a denoiser, we can also actually test this is train, gives us our sample size. Undersampling, is it in config data train? No, it should be from config data val because we validate on the undersampled problem. Okay, so it's kind of starting to make sense. Same, yeah, so everything related to measurements will be validation time. What we do need to get is, so let's call these not val samples. Let's call these, first of all, these are synthetic samples, okay? Because it makes it confusing. Now for conditional, So for unconditional, we start from random noise and we generate synthetic samples. Okay, that's good. But for conditional sampling, we actually have to start from a real batch of validation data. Hey, thanks for the follow. What I'm working on is I'm working on PyTorch. If you're familiar with AI or machine learning at all, or more general GPU computation. But this is part of a sort of an ongoing series I have. I'm actually trying to re-implement, let me show you, I have this paper I did in grad school, and we're basically working on re-implementing it from scratch. And it's a paper where we train a diffusion model. I don't know if you're familiar with generative models at all, but I covered this I covered this on YouTube. If you can find my YouTube channel in the description. So then we have to do the whole thing, because I decided, okay, let's just re-implement my PhD paper from scratch for whatever reason. So then that means we have to write all these equations in PyTorch. They're not as scary as they seem. It's basically just also train a model and then use it for inference. I think I have a nice diagram that I'd like to show somewhere here. Oh yeah, here it is. So then it would be stuff like, you know, we want to do clean coding. We want to make sure the paper works. I know it works because it's been a pretty popular paper. People have used it before. So we want to reproduce the model training and model inference. So then this all goes into a GitHub repo, which is also public, and you know, it's Python coding, so I use UV, PyProject, PyTorch. Pretty good though, yeah, thanks for asking. And it's just a diffusion model paper. All right, so let me get back here. So unconditional sampling, we just generate synthetic data. Now we still need to plot these, because otherwise they don't go anywhere. And let's actually do this. Forget about it. Let's just do it right now. Okay, so let's do a quick plot. So from matplotlib, import pyplot as plt. I don't have matplotlib, but it's very easy. I just do uv add matplotlib. And that's it. And then I like to pin it down to 3.10.8. Okay. Yes, there's a question from YouTube. Yeah, go ahead. You can just ask about neural network architecture. Go for it. Let's see what the question is. And all right, so let's just plot these samples, right? So plot the synthetic data. Actually, you know what would be nice? If the batch size here would be the same for, actually. Damn it, so maybe I do need a config. Do I really need a batch size here? Config val. Wow. The question from YouTube is how can you design a full neural network? Depends what you mean by design, because here that's a good question, because so what I'm doing is I'm using diffusers, which already has the UNet. Where is it? Here it is. It already has 2D UNet models implemented. The problem though is that even these models, so first, they have a ton of hyperparameters. Yeah, okay, that's a good question. Okay, and if you mean it that way, so if you're asking about input-output shapes, yeah, so they're pretty much, solutions are there. For us, for diffusion, we use UNets because they have a specific property. They're fully convolutional, so they exactly preserve the input shape, if you're talking about shapes. So that's a pretty useful property. If you need the output shape to be exactly the same as the input, there are some power of 2 constraints which are related to the depth. So you can check out UNets. Otherwise, if you have to do it yourself, you have to be careful always with convolutions and padding if you use convolutional networks. If you want to change the size to a given one, that is a bit harder. I don't think you can find, you would have to you would have to do that yourself, and it is not that easy. Yeah, actually that's a good question. I don't know how I would do, like, if you need some sort of relation between input and output, right? Like if you want the output to be twice the length of your input, let's say you work with time series, you would have to look at the internals of each layer. I don't know anything for images though that actually gives you that. People usually write those by hand. Usually in convolutions it's done with padding. What do they do? Yeah, because you pad and then the signal spills over the edges after each convolutional layer, right? So you can measure, basically you add 1 pixel after every layer or something, depending on the width of the filter. Somebody on Twitch is, I studied what language? Oh, this is Python, but yeah, it's PyTorch specifically, which is a Python package for, it's for deep learning, but it's also for computing on GPUs. So yeah, you'll see a lot of Torch here, like Torch tensors, if you're familiar with high dimensional tensors. Matrix multiplies are pretty fundamental, random number generation, also complex values. Another thing about the paper I'm trying to do right now is that it works with complex values, not real ones. So there's a lot of conjugates and transposed. So let me see what okay, so I wanted to plot a figure. So let's do a plot synthetic. Okay, so let's plot the synthetic data. So let's do a figure. It's a personal project because I'm re-implementing one of my projects from 5 years ago. So you can call it a personal project. I just decided to redo it all from scratch, cleaner. So let's open a new figure, and we know we'll figure out what the shape is. But how do we get this 4 here? I really would like to have this 4. Okay, I'm gonna do something dumb here. I'll just put it in train config. I'll put it val batch size because I don't want to build another config here. So then we can give to the data loader config train dot val batch size. Okay, so now I can reference this mysterious 4 everywhere. And I can say, I want to generate 4 random samples. Yes, okay. And then I'm gonna plot 4 random samples. So I'm just gonna plot them for I in range this. So we'll do a subplot. Let's plot them all on the same line, I guess. So 1 line, this number of columns, I plus 1. And we can just im show synthetic samples of I. CPU dot numpy. Well, actually, we can plot the absolute value then. Absolute value dot CPU dot numpy. And that's it. PLT axis off because we don't need axis labels. And that's it. We can do a tight layout. And we can save this. Should we save it in plots? Is this beginner friendly? It's moderate, I would say. It assumes what I'm doing right now is more core Python. So I just want to plot 4 images in a row, which is pretty basic matplotlib. But then the paper itself is a bit more complicated. It's related to AI. But yeah, feel free to ask or just lurk around or whatever you want. Okay, so we need to save this somewhere. I have a YouTube series. If you check my YouTube channel, it's like, this is like the 13th episode or something. And usually each episode is like 40 minutes. So it's not too long. It's just a couple of weeks in real life. Okay, so let's save to a folder called models. And let's create it if it doesn't exist. So os make dirs config train dot save dir exist. Okay, is true. I need to import os. I kind of figure it out. I didn't really plan too much. Yeah, I just used that big. I kind of know what I want to do, but I don't really plan. This is just a live stream. So yeah, no, I didn't practice this before. That's why sometimes it ends up being messy. Okay, so we imported OS. So now we're making the save directory. So now we can save. The reason why I wanted to make this is because I want to save the plots here. To save figure. So let's save it to config train.save directory. And let's call it unconditional step and the step number.png. Okay. And the step number, I believe it's called step idx, right? No, step? Yes, it's step. Okay. And we're going to save at DPI 300, bbox inches tight so we don't get spacing, and we can close the figure. Okay, so now at least finally we save the samples we generate. So now we should see data quality go up, hopefully. Now the other thing is for conditional, I think what's challenging is we're not quite there yet. What's going to happen is we're training a model and there are some parameters which we're going to have to get right. And I think that's going to be a bit harder. It's actually what I'm about to do right now, because when we conditionally sample, what happens here is we may get numerical degeneracy. So then I can't even plot this, okay? So plot if everything went okay. The fundamental reason, though, is harder to fix, though, because we'll have to do some experiments to figure out stuff like step sizes and a bunch of these numerical parameters. So if, how should we say this? So if any is nan, this gives me what, a tensor? I think debugging is harder because especially in these types of projects with numerical precision, it can get really nasty. Actually, funny thing is, yesterday on my YouTube channel, I did another live stream and I was really trying to debug another paper of mine from a long time ago, and I couldn't do it in 3 hours. It kind of drove me insane because I actually had somebody complain on GitHub like, hey, this is not working, can you fix it? After 5 years, out of all things. And then I tried to fix it for them yesterday and I couldn't fix it, but then I had to spend more time today to finally get something working. So it's definitely code. You have to be careful when you code so it's clean, because if I look back, this is just VS Code. Yeah, a Visual Studio Code on Windows. If I look back at my code from grad school, it's really messy. Yeah, like I had to struggle yesterday. It's on my YouTube channel. It's in the live section. It's like, it was actually MRI. That's the funny thing, is because I had, oh, actually that reminds me, it was much closer to MODL. because I had conjugate gradient and everything, and I must have messed something up numerically, but I had to retrain a model, and I finally got something working, but it took a long time. Yeah. So that's a pretty funny stream to watch because I get increasingly frustrated. This is gonna okay, so let's go. So now if not, if I can only plot if nothing is nan. My question now is, can I do this in PyTorch? Can I test any? I think PyTorch is still limited here. From Twitch, any tools you find really helpful? Not really. I try to stay away from AI coding. I know all the hype and everything. This is why sometimes it seems boring, but I just implement everything by hand. Yeah, and then of course just a terminal is all you need. Oh no, I will say that UV is my favorite Python tool. If you're not familiar with UV, and this goes for everyone, like you should really install UV. Actually, let me look at this now. I'm curious. Let me look at your thing. What was it? Econometron. I'm very curious if you used UV now or not. See, you didn't. You're still on requirements. You should really look into UV and the PyProject TOML for requirements. But anyways, yeah, that's a different story. There's a question from Twitch: front end or back end? I think it's always back end because it's always low level for me. Like obviously PyTorch itself is super back end, right? It's only for computations. You can't do anything to expose it to a user. Okay, so what was I going? So UV run Python. So if I have a tensor, x is torch randan 4. And I do x is nan any. Can I? Okay, so this is false, right? Yeah, okay, so I can test for equality with, but can I test y equals 1 if x is nan any, else 2? Yes, I can. Okay, good. So this is valid code then, because so if there's no nans at all in the val samples, then we can do the plot. That's it. And the plot will be very close to this one. Well, it's actually very, very close to this one. Except, of course, we keep forgetting to do the real thing. We have to take a batch of validation samples. So what are we plotting here? Val samples. But they're not val samples. They are estimated. They're recon samples. All right. Now what we want is we want to reconstruct the real val samples. I don't have a Discord yet. Yeah, sorry. And we are going to plot recon samples. And we're going to call this conditional. And complex to real. This is where we need the actual val samples, and we need the measurements to be actually generated from the. So now we got to replace the init back with val samples. Gotta be careful here. Okay, here we go. Okay, so now we finally need to, well, let's get the val samples here actually, right? So get a batch of validation samples. Yeah, thanks for stopping by. Thanks for chatting. Val samples. It is a okay, so hang on. So let me get the val samples, which is just next iter val data loader. Why did I have this 0 here? Oh, I see, because I use a tensor data set. Ugh, it's so annoying. Okay, so now we have validation samples and we pass them to the conditional. And finally, we can also measure reconstruction error, which is finally the goal in our paper, right? Because we can say, first we plot, but we can say recon MSE equals, this is just torch linalg dot norm. We can just immediately do this. Recon samples minus val samples. Oh, whoops, not here, sorry. Recon minus val samples. Gotta be careful with the norm here though. Actually, let me do this manually because there is a trickery here. Torch sum. If you do the norm of a matrix, it actually does the singular value norm thing, which sounds really bad. Instead, we want to manually do the mean squared error, so this, or the squared error. So torch square absolute values of the difference on dimensions -1, -2, because these are supposed to be complex. -2. Okay, finally we're done. UV run pre-commit, run all. And then we can track. We can just print validation step, whatever it is, step, MSE, recon MSE .cpu.numpy. Okay, so we're gonna get a nice print and everything. And I can actually launch a training run, UV run -m mymo.train. There's probably gonna be a few hiccups, maybe not. Okay, all right, so not too many hiccups. Validation works. Now, of course, it's gonna sample. Okay, so yeah, we'll wait for this to finish. Let me show you. We'll wait for this to finish. Let me show you UV though. It's yeah, it's a Python package manager. It's basically like virtual env or like Conda, but like the modern version. Because you may have noticed that I launch all my scripts with UV run. And it also works with PyProject. And it's like it can manage Python installs by itself, so you don't really need to install Python. You don't need to install different versions of Python in the system. You can just swap them around on the fly. Because then if you look, actually in previous episodes, we had some nasty dependencies because there's this Siona generator, but it's not compatible with PyTorch. It uses TensorFlow, and there's some NumPy 2.0 conflict. But then you can declare dependency groups, and you can declare them as conflicting. So yeah, it has a pretty advanced let's see what happened here. The save directory is not a path. Oh, it's not a path because I need to make it a path. Okay, path models. Okay, well this waiting for sampling is kind of annoying. Let me do this trick I used to do. So if step +1. Yeah, and it also solves all the dependencies for you. So for example, you know, if I want to add, let's say I want to add matplotlib to the group Siona, because I don't know what these guys did here. Maybe they want a different version. So then it automatically figures out and it adds it to the dependency group, right? So you can create a dependency group for Linux, one for Windows, and it'll figure out everything, or different versions of packages if you want. You can then add optional dependencies, blah, blah, blah. I'm just gonna remove this because I don't really want Siona. Matplotlib in Siona. Okay, so we do this +1, so we don't really plot in the first try. Sampling verbose. Let's make this every 500 steps because I want to train the model a bit. But in any case, we're pretty much done here. So we can do UV lock, PyProject, SRC, sampling, SRC, train, git commit, use validation data. And I think we have the whole pipeline now. Okay, so we can push upstream, conditional sampling. There we go. So now let's launch another training run, which should train for longer now. And I think I swapped groups, and of course I forgot. I should have done UV run with the group torch. This is another thing. So I run -m MIMO train. And that's it. It figures out the dependencies and it runs. There we go. So now it runs with PyTorch. Oh, there's a typo here. Loss function at step, not on at step. Okay, loss function at step 0, blah, blah, blah. Okay, loss is going down, so we're definitely learning the prior. Now it's all a matter of, did we get the step size right enough to not get numerical degeneracy? I doubt it. I really doubt it. Where the heck did I even put the step size? Oh, in sampling, of course. And what did I use for alpha 0? 10 to the -3. I think this is not good. Okay, so first of all, my training is not even that smooth. Yeah, from here on now the hard part begins, where we actually I have to reproduce the paper, and this is pretty bad because the training is already unstable. Is my learning rate too large? Not really. It's 3 times 10 to the -4. Very curious how the samples look like. Okay, it is going down. Okay, so at least we're pretty clean. Then next we can work on logging, like systematic logging of all these things instead of printing to console. And the better CLI, command line interface. Yeah, but we need to wait for the model to go down now, which is not the easiest part. What batch size am I using? Oh, 16 is way too small. And there is a latency too for sampling, I guess. We have to wait a minute. But I'm very curious how the samples are gonna look like. I suspect they're gonna look like junk. Although there is some structure, yeah, there's a lot of things to fine tune. The other way we can do it is systematically with some library like, that is correct. It is, you're right, it's exactly right. For the inverse problem, it is unsupervised because it only learns to denoise. It doesn't learn anything during training about the inverse problem. We're just applying it, which is why those inference parameters are pretty nasty. They have to be tuned by themselves. In a way, that's good because they're decoupled from training, but I remember from my grad school days it is very sensitive and you'll get numerical degeneracy. So how can we make that? Now, what I was going to say is there is this Ray tune library, which you give it an experiment and it... Ah, come on. Okay. I knew I had tensor issues. Ah, because I never moved the samples to GPU. My bad. So val samples to almost there. Model.device. This is how we move them, right? Yes. Actually, this should be model.device, not config. Let's see, where else do we use device? Yeah, we should always use model device to make sure everything stays, except obviously for the model. Okay, what I'm gonna do is I'm gonna skip the unconditional one because it takes, well, actually, wait a second. Oh, you know what? These, oh, here's the samples. I gotta tell you, these are not too bad. This is not Gaussian noise, right? There's some sort of MIMO clusters in here. And actually, let's do this. Why don't we plot the 4 real ones on top? So we sort of know how they look like. Again, validating these is a bit hard. You need a bit of domain expertise, but this is actually pretty, well, it's pretty bad, but there is, I'm seeing some, I think I see some structure here. You can see some patches here. So why don't we do this then? Because this is also interesting. How the heck would you ever debug this? Even for images, right? You would have to just look at them. Now there are metrics for images, like perceptual metrics for whatever neural networks. But for channels, it's even harder because unless you're used to, which I kind of am a bit, that's why I recognize them. But let's do it this way. Let's plot instead. Let's leave the synthetics in and let's plot 2 rows. And on the top row, okay, so here we skip. Let's make this the bottom row. But then on the top row, let's just plot the 4 real samples, which have no relation to the synthetic ones, but we can sort of see how they look like. Okay, so let's make this im show. Aha, this implies I'm gonna need these faster now, okay? So let's get these at the beginning. Okay, so then I can just plot these because I know they have the same shape. Yes. Okay. Now we fixed a few more things. We should be good to go now. Let me delete this. So let's try again, and we're back to the waiting game now. But this is not the worst. If I see structure, then it's only a matter of tuning the alpha parameter, which I remember is the most important one. I can look at my old code to see what it is, but I don't want to spoil it for myself. Yeah, I would like to rediscover this. This seems okay though. This seems pretty conservative. Maybe DR, maybe my decay is too fast, too 0.99 noise level decay. So what do I do if what do I get if I... No, but it should be fine because we did this calculation, right? If I... what is 0.99 to the power of 1,000? Yeah, this is my terminal noise power. So this is basically a noiseless signal at the end of the sampling, which is what you want. So then my noise starts from 10, which overtakes the signal completely, and it decreases exponentially. Well, that's what it should do in the sampling chain. Of course, while still reconstructing, which is all up for debate if it actually works or not. I'm not happy with this training though. The training is really bad. 3 10 to minus 4. It's my batch size. It's too unstable, right? I think I remember this. Yeah, if I make the batch size larger, the training will be more stable and it'll go down. But maybe this is what we want. I would like to systematically experiment with all these. Okay, let's just see the plot at least working. If I get another PyTorch error, I'm going to be upset. Let me just preemptively, let's look here to see what we have. Matmul, this is CUDA int, undersampling, CUDA. What's going to happen is we'll get nans though, so we'll probably won't even see the plot. Noise, how much noise do we add? Very little, right? I think. Yeah, 001 is very small noise because it's squared in power. And then my signal power is 1 because I normalized the data. So then the SNR is like 40 dB or something, which is pretty good. Like it's pretty much pristine, right? So it's only a matter of undersample. Now I can make undersampling 1, right? Which will give me a very easy inverse. Maybe we should start with that then. Maybe let's do that. That's a better idea, right? Because now we get 6464. So we get exactly... Actually, this is a very easy problem now because it's 1 and with low noise. Okay, I got again. Ugh. Where? Why? It's gotta be the last thing, I swear. 153. Yeah, the funny thing is I think I omitted some stuff from the... This is... Oh my god, I need to do val samples equals. I don't think I even say the value of alpha. That's the real problem in the paper. And this is why I'm doing this, because I know it's in... What you have to do is you have to look at the original code under the UTCSI lab. There you'll find the real values, but the code is very, very messy and it's really not clear how I even got those values, which always upset me. Okay, I'm gonna skip the unconditional for now, but we can see what it did at... Okay, my plot size is screwed up. The channels... Yeah, okay, they don't... So this is how they're supposed to look, like the top row. Obviously, they're not there yet. Also, my figure shape is out of whack. So let me just do a no fig size for now. No, let's just do how they want it to type. Okay, again. I don't think I even say what the alpha is. Maybe I do say what the... Actually, wait, you're right. If it does say... wait, the paper is fair game. Wait, why am I doing this? I should... Do I say what alpha is? I'll bet you I don't, which is a big mistake in the paper. So we train on 10,000 samples, mixed, NMSC, 3. No, it's not to be confused with this alpha, because this is the undersampling, which is also bad for the paper. I should have used different notation. See, that's the thing. I don't even say which alpha I used. Yeah, but that's the undersampling for us. I'm interested in the algorithm alpha. It's not the same. It's alpha 0 is what I want in algorithm 1. This is another mistake in the paper. And I did not say what alpha 0 is, which is really bad. So this is exactly why I wanted to reproduce this though, because See, I lied here. It says the scalars are discussed in section 5. And I never mentioned what they are. But if you look at the original code, there is some code that finds them in a systematic way by a grid search. So yeah, so this is the big gap. I would like to rediscover these without looking at the other code. I know how to do, I mean, the thing is, I remember how I did it. I did it by brute force. I just did like a grid search. Yeah, there's an omission in the paper. Oh, no, wait a second. Is it because this is the archive? Wait. Is it because I did not update? I wonder if the official paper is different, but I don't have IEEE access to it. If you look at the actual published paper, I don't know how to get it though, that's the problem. Maybe an NSF. Ah, it says that? Where does it say grid? Yeah, it does say grid. So that's the thing. I do say it's a grid search, but I never say what the values were. So basically we'll have to redo this. There's no other way. I don't think there's a principled way to do it. Okay, so what happened here? Sampling exited early because of NaN values after 100 sampling steps. It's not the worst. Okay, so everything works, okay? So we can clear this. We can re-enable this. Whoops. So now we have full training and validation, and with sampling, and with inverse problems, which is pretty good overall. What did I change in the lock? No. Git add UV lock src MIMO data. So now it's just a matter of monitoring the performance, end-to-end validation, which is nice. We can do that next episode. Yeah, okay. All right, so now we have the full pipeline. We can just launch a run. Now what's gonna happen is it won't plot. Unfortunately, it will not. Let me delete the models folder. It's likely it won't plot the estimated samples because they degenerate to not a number. But then you never know. If we let the model train for long enough, it may get better, so it avoids numerical degeneration. But in any case, the pipeline is full now. It's actually full now with inverse problems and everything. So it's just a matter of finding the exact values in the paper, and I think we're pretty much done. Then we can work on improvements, and we have to clean up the interface. But yeah, if you're watching on YouTube in the video, thanks for watching, and stay tuned for the next episode. All right, so that was the YouTube cut. Yeah, this is not too bad. Not too bad. I'm tempted to use, okay, so let's try to plan ahead now. So we can do a grid search, but even a grid search is sketchy. What if I use Ray Tune? This is supposed to be fully automated. Like, you give it your function. So we can functionalize all the training, which is already there. Like, you just give it the main loop and you return a score. All we need is to return a score, like a goodness score, right? So it can just be this recon MSE, because that's what we want at the end of the day, right? The interesting part is, if we see a NaN, we should set this to a very high value. And then what this Ray thing does is it uses Bayesian optimization on top of everything to just automatically tune hyperparameters. And I think this is not a bad thing to do. I think we want this. And I think we can do a trick where we just tune these early. We don't need to wait for the full training run, maybe, because for now I just want to stabilize. I'm not sure. Yeah, it's gonna be. Yeah, it's either grid search or we'll do it with Ray. So that's one thing. The other thing I want to do is I need to clean up these configs, because right now users can't specify them from the command line. So this is pretty annoying to change all these. Now these things are also involved in training, and they will have to be hyperparameter tuned as well. Num noise levels can be 1000, but the starting noise and the decay coefficient for sure has to be optimized. Batch size, I know it has to be larger. Actually, let me do that then. Let me retry a run. Maybe there's a trickery here. What if I do like 128? It's not a VRAM issue because the data is very small here. So now technically I'm training for long, I'm seeing more data between validation runs, right? Because my logic, I don't have epochs in my logic. I just use step logic, which is probably a bit inefficient. Let's see if the loss goes down more constantly now and to lower values. Maybe, maybe not. I don't understand why it's... Yeah, exactly. Ray does all that. Yeah, Ray actually does it. You can dispatch it to parallelize. Although I only have one GPU though, unfortunately, so it's not really gonna work if I search over training runs. I can only train like, I mean, it's not a RAM issue, but it's like I'm training at 100% usage. But yeah, okay, it seems this stabilizes training a bit. So larger batch size makes the train loss consistently go to lower values, which is good. Yes, okay, so no more jiggling. Okay, so this is good. This matches theory, right? A larger batch size with more data, that should be better. The thing is, the denoise, this is basically a measure of how well it's denoising, and compared to the random network, it's not there yet. Ah, okay, it's already unstable. I have a 3090 with 24 gigabytes. I think, let me see how much a run uses. But it's not a RAM issue because, well, it uses like 6 gigabytes, so I can launch 4 of them, but I'm already drawing power, so they'll just slow each other down proportionately, which is not ideal. That's because the code is already pretty efficient, I'm guessing, so it uses the GPU pretty well. So yeah, maybe it's just a matter of letting the model get to lower lows. Interestingly, this is something I never did. I never tested the inverse problem performance during training. Oh, 2 gigabytes of VRAM. Yeah, that is little. Yeah, you can't do much on that, unfortunately. It's probably better to do it on CPU. Okay, now it started the conditional sampling, the inverse problem. Please don't degenerate. Do not degenerate. It degenerates at step 100? Why always at 100? Why? Yeah, there's some structure here, but not too much. Top row are real samples. The bottom row is supposed to be synthetics. Let me wait for another batch because I don't like that. Why does it exit that sample at step 100 in the diffusion? That seems, did I mess something up here? What did I do here? So measurement noise, pilots, sample. Oh, I wonder it's because I divide. Okay, there's another thing. I didn't make the model noise conditional because I'm hard coding time step 1, but it's just a neural network. Okay, so I'm basically have to recreate the whole stability, but this division is kind of sketchy though because this is a very small value. I think this blows up to it. So this is small, and then this becomes much smaller during sampling. So it's gonna be times 10,000 basically, divided by 10 to the minus 4. Yeah, we'll have to debug this. We'll have to do some numerical analysis. Okay, the other thing I can do is pick a better model architecture because this UNet also has a thing called time step, which I'm not using. Then we get into the whole time embedding thing. Yeah, so there's a bit more work to do to stabilize this. Okay. Interesting. So I have a unit. So what does it want for forward here? Time step, union torch tensor float int. I'm gonna need to pass the proper time step because I pass time step 1. What do you mean by Gaussian? Adding it to what? To the time step embedding, or? Okay, it also exited at 100. I mean, what's happened? Oh, okay, the training finished because I only have 1,000 steps. Okay, let's do this then. The randomness. I have the noise here, but it's the problem is this thing decreases, and this is fixed. This is 10 to the minus 2 raised to power 2 is 10 to the minus 4. This thing goes to 0 in the sampling process. We do add it back, but this is gonna blow up numerically, I'm suspecting. Yeah, so we have this. Yeah, it's the average plus this is it, right? Plus we add it back. Yeah, this is the divisor. Yeah, the measurement plus the noise. Interesting. If I take this away, I don't understand, because if I have very good data, should I blow up this term then? Eugh, that sounds really bad. So at good SNR, this becomes even smaller later in the sampling process. Something is off here. But what do I multiply this with? Step size. So this also decays it. And this also gives you the outer noise. I feel like all this stuff should cancel each other out, right? Because the noise levels decay exactly at this. Is that true? They decay at rate R? I think it is true. Okay, so maybe this is not too bad then, because this decays at rate R, but then it gets multiplied on the outside with something that also decays at rate R. So I don't know, this will be more stable at... I mean, I can do a stabilizer here. Nah, but it's gonna ruin the step size of the algorithm and everything, right? There's no way a stabilizer here will work. Let me see here. Can I pre-compute these schedules? I think this would help. Maybe we can next episode we can re-architect this a bit, because actually I'd like to see what these all are on the outside. I think that's what I'm missing here. Yeah, okay, because there's no reason to compute these here. Well, the thing is, I know this is 10 to the minus 4, so it's already capped here. This is basically 10 to the minus 4, right? So then it won't matter. That's the thing. This is a stabilizer. So anything I add should be more than it should be more than 10 to the minus 4, but then it doesn't make sense to add like if I add 10 to the minus 2, yeah, it'll. Okay, so we can do this just to check if it's this. I bet you it is this. Well, actually, let's do something else. Let me just breakpoint to see what's happening here. So let me just comment out the unconditional because we don't want to go through the synthetics. But what we can do though next time is we can actually pull all these out, because I can see all these schedules in advance because they're deterministic, right? So that would be helpful to plot them and see which step size, how does noise derivation square root. And I can also compute this coefficient ahead of time, actually. Basically everything that's a multiplier, right? Which will be pretty helpful. And then it's just a matter of tuning the parameters. But then simultaneously, we also have to make... Maybe the bigger problem is, why doesn't training go down? That's related to the way I use the unit, because I really have to use that time step. And it gets into sinusoidal embeddings and stuff like that. Because I use time step 1, but I should really use... So let me see what they do with the time steps here. Time step. Torch ones. Compatible to Onyx. Time embedding. So they get the temporal embedding here from time projection. And the default is, I did not change this, so it is what? I think it's positional or Fourier, I don't remember. Oh, it's here. Positional. Okay, so we're going on positional. So it's just time steps, which is just... Yeah, it's a sinusoidal thing here. So we definitely need this. Okay, so now this should crash at step 99. Yeah, okay, so it did crash. So what crashed? Conditional. Yeah, so it's e to... Okay, so this blows up. It's e to the 35, right? So yeah, so it goes to infinity. Where it's already degenerate. My output, I'm guessing, is fine. Yeah, the output from the network is perfectly fine, but it just can't keep up. Okay, so then my conditional term obviously blows up. Is it... Reconstructive measurements should be fine. Oh... Wait. Oh, I see, because it increases over time. So the reconstructed measurements, because this one blows up in magnitude, yeah, it actually gets farther away from the real measurements, which are very tame. Yeah. Okay. I see. There's also a power amplification here, which I forgot to take into account. Okay, so there are a few numerical fixes to do here because I know what mistake I made here. I made a mistake when generating the measurements because fix me. Preserve unit energy. This actually significantly amplifies the power because this pilot matrix does not have unit energy. It injects a ton of energy in the measurements, right? Because if I look at torch linalg.norm pilots, yeah, it's like 128, the top singular value. It's not 1. So I think this is a cause for degeneration, and I remember this. Yeah. So I'm blowing up the measurements, and then it gets farther away. It tries to take a bigger step. It blows up even worse. Blah blah blah. Okay, well, that's a problem for next time. I think it's I'm gonna stop right now today. Yeah, thanks everyone on YouTube and Twitch for stopping by. Thanks for the follows and subs, and yeah, sub to the YouTube channel because I'll cut some episodes and I'll post them to the series if you ever want to rewatch. All right, I'll stop. Thanks everyone. Bye.